Okay.
Yeah.
Turn on. Trying to turn on. It's on. All right. Very good. So it seems like it quits out at the beginning of our class after being on all day long. That's we're going to have to replace that. Okay, there was some requests to talk about some explosion problems. You have conservation of momentum explosion problems. So in your homework, you have a firecracker problem. So let's talk about that. Let's do an example. Let's say a firecracker is initially at rest. Okay? Let's say it breaks apart, breaks into 3 pieces. Okay, the first piece, let's try to abbreviate this. It has a mass 0.30 kilograms, velocity, let's give it a name, VA is equal to 10 meters per second, comma, 25 meters per second. Let's make it 3-dimensional. We don't usually do 3-dimensional. Let's give you a z component as well, and 5 meters per second. Let's say the second piece, and I have that being a mass 0.40 kilograms, and it has a velocity VB, and it has components negative 20 meters per second, negative 10 meters per second, and 5 meters per second with a positive sign. The question is, we have the third piece, and it has mass also 0.40 kilograms, and we want to know what is its velocity, VC. Okay? So, let's do this problem together. Oh, I have to make that actually. Wait, it was working now. What's it doing? Okay, here we go. All right, so how do we do this problem? Somebody tell me how to do this problem. Yeah. Yeah, you guys want to come or something else? Yeah. Yeah, exactly. Both are saying the same thing. Okay, so we're doing conservation of momentum. So the total initial momentum must equal the total final momentum. So conservation of momentum. Right? If it's complicated, just note that the only thing we really do with momentum, we only do 2 things with momentum so far that we've done. One was about impulse, right? Remember, you have a force that smacks a baseball, and you do the integral of the force with respect to time. That's the change in the momentum. Remember that? Okay? Integral of force with respect to time is the change in momentum. The only other thing we do is we say conservation of momentum. So if there's the word momentum or there's momentum involved in a problem, it's one of the 2, and it's pretty clear which one it is. Okay? So conservation of momentum, so we start off with the total initial momentum. Okay, and that must equal the total final momentum. And so what is the total initial momentum? 0, because it's at rest, momentum is mass times velocity. It's at rest, so 0. Okay? And now we're going to find the momentum of each of these pieces and then add them together. The VC we obviously do not know, though. Okay, so we have the 0.30 kilogram mass. That goes with the velocity VA. Let's write it like this. And then we have the 0.40 kilogram mass, the thing in the middle. And so that goes with velocity VB. And then we have the 0.40 for velocity VC. Okay? Everybody's with me on that? Very good. Okay, now I'm going to do this using components. We have 10, 25, 5, negative 20, 10, 5. So I'll put these guys in. I'll write it like this. I have 0, 0, 0, because that's the 0 vector. Okay. Then I have 0.30 times each of these things, 10, 25, 5. So I'm just pulling down this vector here and putting it there. Okay. And that's VA. And then we have 0.40 times, now we're going to take this vector here, VB, and put it down here, negative 20, negative 10, and 5. Okay? And then we'll have 0.40 times VC. Any questions about this? Okay. Now, so we have on this side all these zeros. We know that these are zeros. And then we multiply 0.3 times 10, so we have 3.0. We have 0.3 times 725, that gives me 7.5. 0.3 times 5 is 1.5. Then I have 0.4 times negative 20, that gives me negative 8. And then we have 0.4 times negative 10, that gives me negative 4. And then we have 0.4 times 5, that gives me positive 2. Okay? And then we have still the 0.40 times VC. Okay? Now we can add these two component by component. This is just vector addition. So we have negative 5, comma, 7.5 minus 4.0 is 3.5. 1.5 plus 2.0 is 3.5 plus 0.40 VC. This is equal to 0, 0, 0. So now we can solve for VC. We can say VC is equal to bring these to the other side. So we'll have flip all the signs of these things. So if you want, put a minus 5 in front. Minus 5, 3.5, 3.5, divided by 0.40. And then I end up with 12.5 meters per second. And then negative 8.8 meters per second. And then another negative 8.8 meters per second. Okay. Everybody good on this? Conservation. All right. The problem may not have that the initial momentum is 0. It seems like a lot of the problems we do, initial momentum is 0, but you might be given the initial speed of the firecracker. You could do a problem like this, right? You would just say the mass of the whole firecracker times its velocity would go on this side. Okay. Questions? Questions? All right. Let's also cover another topic that's on your homework. Okay. So remember, there's this big long assignment, like tradition every Sunday. You have this big long assignment that you have to deal with. Now, one of the problems is these conical pendula. So let's consider a conical pendulum. Okay. If you're wondering what a conical pendulum is, it's just basically you have a string. Here's the string. And you have a ball. You swing it around in a circle like this. Okay? So it's going around a circle. And so I can draw, this is a vertical line to the center of the circle, and I can call this angle theta. Okay, so here is my ball. Here is the string, so there's some tension that, t. Okay. And let's say there's speed is equal to v, and it's going uniform circular motion around the circle. And then we have some radius capital R. Okay, so the ball moves around with uniform circular motion. Okay. And I'm going to derive a relationship between the angle and the required speed of the ball. It will also involve the radius. Okay, so what do we know about uniform circular motion? We know that in order to go around a circle with speed v, with the mass m, with the radius r, that there needs to be a net force, right? And that net force has to be what formula? Y times what squared over what? Yeah, mv squared over r, okay? So for this comic, because it's a uniform circular motion, we must have that the net force is F net is equal to mv squared over r, pointing towards the center of the circle. Okay. Now let's take a look at what's going on with this ball. So I have the ball here, and then we have a tension pointing like this. That's one force on the ball, and it makes an angle theta. And then we have the force of gravity going straight down. That's Fg, which is equal to the mass times g. Okay, so now we have the ball. Here's the center of the circle somewhere over here. Center of circle. Okay, and so the slightly complicated thing is, notice it has to point exactly towards the center of the circle. So it's a horizontal. The net force has to be pointing in the horizontal direction. Does everybody follow that? Okay. So if I draw some axes, if I call this positive x, positive y, and this positive x, then what we need is the net force to be pointing only in the x direction and pointing directly towards the center of the circle. Okay. Questions about this? Pretty good. Okay, so let's now, we can start anywhere. Let's start off with the y direction. Okay. You might say, well, how do you know to start off with the y direction? Well, it turns out to be slightly easier to start off with the y direction. Okay. But it's not the end of the world if you start off with the x direction. You can get the equations in different orders. Okay. So in the y direction, we know that there's no net force. There's zero net force in the y direction because I'm saying the acceleration must be pointing towards the center of the circle, which is horizontal. Okay? So we have the net force in the y direction is equal to 0. Now let's look at what we have here. We have, this is going to be the component of, the vertical component of t. So we will have t times the cosine, right, because of the adjacent side here. We have the cosine of theta. And then we have, because this is going down, we have Fg, which is equal to m times g. And since this is equal to the net force in the y direction, it's equal to 0. Okay. Does everybody follow this? Make sense? Okay, yeah. Okay, yeah. This is the slightly complicated thing about this is the circle is in the horizontal plane. It just, I have a string here, and Give me a second, I'll try to find something that goes with this. Good. It's been here on the desk like every other day. But we're doing this. The ball is going around in a horizontal circle. So the net force has to point towards the center of the circle, but the circle is horizontal, so the net force is a horizontal force. There's no vertical force. That's why the net force in the y direction is 0. Okay? And so these must balance out. So we end up with that t cosine of theta is equal to mg. And so t is equal to mg over cosine theta. Okay. Now, usually we plug in numbers and then calculate things and get values. But on the upcoming quiz, you will actually have to work with things that look like this, leaving variables in terms of their names. Okay? Hopefully that's not a source of stress. It's not that complicated. Okay. Now, suppose I were to ask you this tension. Let's see if we can understand this formula. Let's say the angle is some angle as shown. Is the tension going to be bigger or greater than the weight of the object?
Greater.
How do we know it's greater? Yeah, so you guys are giving beautiful physical answers. That's exactly right. Because it's doing more than just supporting the weight. It's also providing the inward force, the horizontal force. Okay. Now you can also see it with the math here. After we solve this for the tension, is the cosine of theta, is that, can that be bigger than 1? In fact, if the cosine of, if theta is equal to 0, what is cosine? 1. Okay, so that's the maximum it can be. But because we've drawn it with, it's not 0, clearly the cosine of theta, for the example, if you assume that the drawing is accurate, we don't try to fool you with making the slant if it's not a slant. Okay. Then the cosine of theta is less than 1, and so this will be greater than the weight. Does that make sense? Okay. So when you look at these formulas, it's good to just understand things like this, that the tension would be greater than the weight of the object. Okay, so now we're not done. We would like to know something about the tension. We would like to know something more about the system. I would like to know how fast it will be going around. Okay, so for that, we're going to look in the y direction. So in the in the x direction. The x direction. In the x direction, we said there needs to be this force pointing in. You can't see that. There needs to be a force pointing inwards towards the center of the circle. So that's in the x direction. So we need the net force in the x direction to be equal to mv squared over r. Okay. Let me just see if I can get rid of some of. Yeah, I don't know why I have this black bar here. I don't know how to get rid of that. Yeah, I don't know. Okay, so we need net force in the x direction to be mv squared over r, but now let's take a look at what forces we have in the x direction. So we only have this force here, okay, or I could have drawn it up there if you want. So that's, maybe up here is a little bit easier to see because I already have the angle there. So it's going to be t times the sine of theta, right? Everybody got that? So f net x is equal to t times the sine of theta. So we have f net x is equal to this, and it's also equal to that. So we get t sine theta. Oops, this is starting to run out, I guess. No, it's fine. T sine of theta is equal to mv squared over r. Okay? But we had a formula for t. What did we have before? We found before that from the y direction, it was mg over cosine theta. Okay. So let's get rid of t. Okay. Let's get rid of t, put it in there. And then we'll end up with mg over cosine of theta times the sine of theta is equal to mv squared over r. Okay? I didn't really explain what we're looking for here. I'm just trying to figure out what's going on with v. Okay, so let's try to simplify. So the m's cancel, which is nice. Okay, m's just cancel. And what's sine over cosine? What's another name for it? Tangent. Okay, so we have g tangent of theta is v squared over r. That's kind of cool. Okay, so the formula for this conical pendulum is g tangent theta is v squared over r. So the tangent theta times the 9.8 is equal to v squared over r. That's how fast the thing, so if you solve for v, that's how fast it's going to go back. Okay? Questions about this? All right. Now there's another type of problem that you will encounter in the homework as well. There's something called a banked curve. And all right. So banked curves are tilted roads to help cars, or it could help bicycles if you put it on a bike track, or even runners, to help cars navigate the circular path. Okay, so what's going on here is you have this inclined plane, essentially, and it's at some angle theta. And then you have, here's your car, tires here, and you have, let's see, let's drive a little car here. Okay, so now we have, because it's an inclined plane, we have the force of gravity going down like that. Okay, so we have Fg equals the mass times g, and times g. Okay, and then we also have the normal force. Remember the normal force from the inclined plane like this. And so we have an angle theta there. That's our normal force. Now, notice that this looks a lot like this. You notice that? The conical pendulum? You have the tension here, you have gravity, you have the normal force, you have the gravity there. So we make the connection for a frictionless banked curve. The normal force Fn acts just like, that's just like the tension in the conical pendulum. All right, so we don't have to, we can stop there. It's the same analysis. We could say we have that here's the center of the circle. We could do exactly what we did before, but most of you would be bored because it would be exactly the same. And we'd say the net force is pulling in the horizontal direction. Okay, vertical components must be sum to 0, and you do the same thing again. So you then would derive the formula g tangent is equal to v squared over r, the same way. Okay? Any questions about this? Yeah. Yeah, okay, yeah. That's something from, you're talking about these two, right? Yeah. This is, This is something I covered in this little extra lecture back Thursday, a couple weeks ago when we did the incline plane. So if you have an incline plane like this, and if you have, I'll try to do with my line. So here's the normal vector, okay? So notice that when the incline plane is flat, the normal vector is perfectly vertical. But as I start to tilt, notice the normal vector tilts the same amount as the incline plane is tilted. So if I go all the way to 90 degrees, the normal vector is 90 degrees away from vertical. So if it's 45, the normal vector is 45. If it's like 10 degrees, the normal vector is 10 degrees away. So yeah, the normal vector with respect to the vertical is the same as the horizontal to the incline. Okay? Yeah, that's actually an important thing. If you didn't know that, that's a key point to inclined planes to get that. All right. Other questions? All right. Let's do a few questions. Okay, again, I'm going to not read it out loud so you can practice your reading skills. Okay, I'll open up the polling now. Okay. You need more time? Okay. So, by the way, as I said in the beginning, if you're looking for the video for the solutions to the practice quiz, it's in the folder with the practice quiz and the practice quiz. It's not in the lecture notes. It's separate in the folder with the practice problem. The practice quiz. Practice quiz 3. Okay. Everybody had a chance to respond? Okay. And 5 more seconds. Ready? Okay. Let's see what people said. All right, a lot of people say C. Let's take a look. Okay, so let's draw some axes here. Okay, let's go in the x direction. What do we know in the x direction? We simply have, there's going to be this F here. Okay, we have the normal force of the wall pushing back. Now, let's draw all the forces at once. Let's just do the whole thing. And then we have a force of gravity, that's Fg. That's equal to m times g. We can calculate that later. Then we have the force of static friction. If there was no friction, the thing would fall down. Okay. So the static friction force is pulling it up. It's going in this direction. That's the force of static friction, Fs. Okay, if you look in the x direction, though, we have Fn is in the positive direction. And then we have F is in the negative direction. And what is the acceleration in the x direction? Nothing. 0. Okay. So that means that's equal to F net x, which must be equal to 0. Okay. So that means that F is equal to the normal, the normal force is equal to F. That means Fn is equal to F, which is equal to 410 newtons. Okay. And that will help us get the friction force. All right. So we want to, so what we're trying to do is we're trying to find the static friction force, okay? And what we're doing is we're saturating it, so we want to say that we're setting the Fs is equal to the Fs maximum value. Okay. And so we know that the maximum static friction force, what's the formula for that? US times Fm. Okay, so we can just calculate that. US times Fm, so that will be 410 times US. We can put in the newtons later. Don't worry about that. And now let's look in the y direction. In the y direction, we have Fs is going up. So we have the 410 US going up. And then we have the force of gravity going down. And that's minus Fg. And then there's no, there's no acceleration in the y direction, so that must be equal to 0 as well. So that's m times g, which is equal to 8 times 9.8. 9.8 is 78.4. And so we get that US is 78.4 divided by 410. And that comes out to about 0.19. Okay. Any questions about this? Pretty good. Is it clear to everybody that if you pressed harder, it would still stay, right? If you pressed harder, then we would not have that Fs is equal to Fs maximum. The static friction force would be less than US times the normal force. Static friction just does enough to make it not move. Okay. All right, let's do one more together so that it doesn't take too long. Let's do a hard one, all right? We'll do a hard one. Since we'll do it together, it won't be a collector question. So as I said, sometimes the problems will combine things we had from last quiz and this quiz. So here's an example of such a problem that's kind of a little challenging. So this is from 2B, practice quiz 2B. The practice problems that I posted myself, 2B, number 13. All right, here's an example of a problem that involves the new stuff and the old stuff. So a 0.3 kilogram ball dropped from 1 meter above the floor, bounces off the floor, and returns to a height of 0.8 meters. Okay? In other words, I drop it, it bounces, and it only comes up to 0.8. Okay. What was the impulse, the magnitude and direction? This thing's a little slanted, sorry. The magnitude and direction that the floor applied to the ball. So we want to know the impulse. Remember, the impulse is a change in the momentum. Okay? So I'm going to now flip the sheet, but remember, the ball is 0.3 kilograms. So we have a 0.3 kilogram ball. It's dropped from 1 meter. So it's dropped from rest. And then it bounces off the floor, and it only comes up to 0.8 meters. So when it bounces off the floor, it will have a slightly slower speed than when it just strikes the floor. You know, it will go down with a certain speed, but it will actually not come up with quite the same speed. This is actually how real balls bounce. They don't, like a basketball. If you drop a basketball from 1 meter, it doesn't come up to 1 meter. It's a little bit short. Okay, so everybody think about whether you know how to do this problem. You have all the tools. You have to put it together, though. Okay? So we need uniform acceleration. So don't type uniform acceleration, all that stuff in your head, and throw it away before quiz 3. That should be in your head. Okay? So we have to figure out what is the velocity of the ball just before it hits the ground. Okay? And then we're going to figure out the velocity of the ball just after it hits the ground. And we can figure that out from the following. Okay? So it's falling. It starts, remember, this is a ball, 0.3 kilograms, starts from 1 meter above. So what we're going to do is, and it starts from rest. Remember this formula, 2a x minus x0 is equal to v squared minus v0 squared. Okay? We'll do this in the y direction. So 2ay times y minus y0 is equal to vy squared minus v0y squared. Okay? Everybody remember this? Old friend? Okay. So you're still supposed to know how to use these formulas. Okay? Review this. And so now it drops 1 meter down. So y minus y0 is minus 1. Ay is negative 9.8. So 2 times negative 9.8 times negative 1 is equal to vy squared. That's the final speed just before it hits the ground. And minus 0 because it starts from rest. So we get vy is equal to negative 4.43 meters per second. It's negative because just before it hits the ground, it's going downwards. Okay. Any questions about this? This is the old problem. You drop something 1 meter, how fast is it just before it hits the ground? Okay. So it's 4.43 meters per second. It's pointing downwards, so that's why there's a negative sign. Now, when it rebounds, when it bounces, let me move this over, the sink is getting in the way here. When it bounces, we're told that it comes up to a maximum height of 0.8 meters. So in this case, we know the final height, okay? We don't know the initial velocity. This is what we don't know. But the final height, at that point, the final velocity is 0. So we'll do the same sort of thing. 2ay times ay minus y0 is equal to vy squared minus v0y squared. Okay. In this case, it rebounds and it comes up a distance of 0.8 meters. Questions about that? Because it starts from the ground and it comes up to 0.8 meters, so that's why y minus y0 is 0.8 meters, and ay is still negative 9.8. The final velocity will be 0 because that's the maximum height it gets to. It's instantaneously at rest. The initial velocity is the thing we want to know. How fast was it going just as it's bounced off the ground? Okay. The reason we're stopping and starting just before and just after it bounces off the ground, because the thing it does on the ground is really complicated. It's a ball that has, maybe it's made out of squishy elastic material. We don't really know exactly how it's going to bounce. We'll learn more details about this later. But this we have no laws of physics to describe at this point. So we're just looking at the free fall and the bounce up. Okay, so now I solve for v0y. We end up with positive 3.96 because it's positive because it's going up now. Okay. So what do we know? We know that vy just before it hits the ground is minus 4.43. Just after it hits the ground is plus 3.96. So we can calculate the impulse. Right? We can calculate the change in the velocity if you want. That's maybe the easiest way to do it. The delta y, vy. Okay, delta vy is the final minus the initial, so 3.96 minus negative 4.43, and that's 8.39. And so now we can get the impulse. That's the change in the momentum. The mass doesn't change. So delta py is the mass times the change in the velocity, delta vy. And so the mass was 0.3 kilograms times 8.39. It comes out to 2.5 kilograms meters per second. Okay? Any questions about this? As you can see, we gave really hard problems to students back in this course here. They complained about this. All right, any questions? Yeah. So, right, you should be responsible for knowing how to use the equations on your equation sheet. Right, so if there are gaps, if you need extra things, this should be something you need to know from memory. Yeah, so I'll see you guys tomorrow.